Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 3, Existence and Uniqueness of Square Roots and Cube Roots. Okay, I don't think I've mentioned this before, but a way to think of a square root if you're confused, there is a radical, and this is called the radicand. Okay, so let me explain radicals a different way. If I asked you what the square root of 16 is, what I'm really asking you is, if I had a square and the area was 16, then the square root is asking, what if all this square root symbol means is, if the area of a square is 16, what is the length of one side? So if I have 4 and 4, you know that 4 times 4 is 16, and area of a square is side squared. So therefore, area equals 4 squared, and the area equals 16 when you have a side length of 4. So when you're doing a radical, what it really means is the area of a square is this number under here, and what it equals outside the radical is the length of one side. So now if I go to cube roots, and I put a little 3 over here for my index, and I have 27, for instance, well, that would mean if I had a cube, okay, I have a cube, and the volume equals 27, then I am asking you what is the length of one side. That is what cube root means. The volume of 27, how long is each side? Remember, a cube, they're all the same. Length, width, and height are all equal. So the volume of a cube is the one side to the third power, or side cubed. So if 27 is the volume, I'm asking, or it's being asked, if this is the cube root of 27, it means the volume of the cube is 27. What is the length of one side? And the answer is 3, because 3 times 3 is 9 times 3 is 27. So this is kind of what roots mean in the 2 and 3, by the way. Get into the 4th dimension and it kind of goes out the window. But anyhow, here we go. Here it says to find the rules. So when we look for rules, we look at what we know about both components of the bivariate data. And these are the 3 terms that I have an x and a y, if you will. And there's not much I can do looking at 1 and 1. It could be 1 times 1. It could be 1 divided by 1. It could be 1 plus 0. That doesn't tell me much. Here it could be 3 times 3, which is 9. So I could think, well, maybe it's times 3 every time. But if I come back up to 1, 1 times 3 does not equal 1, so it's not times 3. And we need to look for patterns when we're doing these. And if I think, okay, well, 3 times itself, or 3 squared equals 9, is 1 squared equal to 1? And the answer is yes. And then we check down here, and 11 squared is also 121, so we just found the rule. So now I know 1 squared is 1, 2 squared is 4. Let me change colors for my answers and get rid of all this mess. Okay, so 2 squared is 4. 15 squared is 225. 10 squared is 100, 12 squared is 144. So if I'm squaring to go, so I'm taking a value and I'm squaring it when I go this way. But if I know something over here, what I'm doing is I'm taking the square root to go backwards. Okay, because the square root of 144 is 12. The square root of 100 is 10. The square root of 121 is 11, and so forth. So if I take the square root of 81, I get 9. The square root of 49 is 7. The square root of 169 is 13. So I've already come up with the rule going from left to right. So if I have m becomes my x, so it's m squared. And going back this way, this is my rule. N will be my x, so this will be the square root of n. And there is my rule for part 1. All right, so rule for part 2, again, I could say 1 times 1 is 1. That's true. But 3 times 1 is not 27, so it's not times 1. 1 plus 0 is 1, but 3 plus 0 is not 27. 3 times 9 is 27, but 1 times 9 is not 1. So we're looking for a pattern that will work with all of the givens, and in this case, here's a given, and here's a given, and obviously the ones are given. So if I think 3 times 3 is 9 times 3 is 27, that's what I get, so that must be a cube. So then I cube all of these. So 3 cubed is 27, so that means 3 to the third power, which equals 3 times 3 times 3, and that does in fact equal 27. 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. 11 times 11 is 121, and I need to multiply that by 11 again, and I get 1331. So 1331 is the cube of 11, 11 cubed. And then 10 times 10 is 100, times 10 is 1000. 7 times 7 is 49. 7 times 7 equals 49, times 7 is 9 times 7 is 63, 7 times 4 is 28, plus the 6 is 34, so 7 cubed is 343. Okay, and now let me just erase all my work here so I can do the rest. Okay, so obviously the rule is when I'm going this way, I'm taking the value that's over here and I'm cubing it. So if I have a p, then over here is going to be p to the third power, or p cubed. Now I'm going to work backwards, and I have to say the cube root of something. So what I'm really doing is taking this to the cube root and getting what will be over on the left. So this will be the cube root of q. So we're taking cube roots. So the cube root of 125, again, if I don't know this, I'm going to do a factor tree. 5 will go into 12, 5 times 2 is 10 with the remainder of 2, and 5 will go into 25 5 times. And then 25 is 5 times 5. So my factor tree prime factorization is 5 times 5 times 5, which equals 5 to the third power. So 125, the cube root of 125 is 5. If I do the same with 64, let me change colors. How about blue? If I take the cube root of 64, I want to do a factor tree. And I'm going to factor 64 is 2 times 32. 32 is 2 times 16. And I'm going to stop there because I see 16 is a perfect square. That's 4 times 4. So my prime factorization is these numbers. Well, it's not a prime factorization because these are perfect squares. They're composite still. But my factors including perfect squares is 2 times 2 times 4 times 4. Now remember, when we're doing cube roots, I need 3. And I don't have 3 of these yet, so I'm not going to stop. So that's what we would do if we were thinking of perfect squares. So I'm going to continue here, and I'm going to get 2 times 8. And 8 is 2 times 4, and 4 is 2 times 2. So now I have 3 2's here, which becomes 1 2 outside, and I have 3 2's here, which would become 1 2 outside. So what I mean by that is if I have a cube root of 2 times 2 times 2, that's 3 of them, I can bring them outside and become 1 outside. Because the cube root of 8 is 2. So I have 2 pairs, if you will, 2 sets of 3 of a kind. 2 times 2 times 2. So I'm going to get 2 2's outside, and 2 times 2 is 4. So 4 times 4 is 16. 16 times 4 is 64. Okay. So now they're giving us a really big number, but if we do these factor trees, hopefully you understand what's going on and it makes it easier. So I'm going to start off with 2, 7, 4, 4, and that is even, so I'm going to factor out a 2. 2 goes into 2 once, 2 goes into 7 3 times with a remainder of 1. 2 goes into 14 7 times, and 2 goes into 4 twice. It is still even, so I'm going to divide by 2. 6 times 2 is 12 with a remainder of 1. 8 times 2 is 16 with a remainder of 1, and 2 will go into 12 6 times. So we are making progress here. 686 is even, so I'm going to divide by 2. And I get 343. And that does not end in 2 anymore, so I can't use 2. But if you remember the rule for set 3's, if we have a number with multiple, like ones, tens, and hundreds, different place values, and we add them up, 3 plus 4 is 7, plus 3 is 10. 3 will not go into that, so it is not a factor of 3. 4 won't go because it's not even. 5 will not go because it doesn't end in 0 or 5. 6 won't go because it's even. So let's try 7. 7 times 4 is 28, with a remainder of 6. And 63 divided by 7 is 9. So 9 times 7 is 63. I forgot my first digit. 3 goes into 34. 3 goes into 34 6 times. 6 times 3 is 18. 9 times 3 is 27. Actually, 3 goes into 3 once. Why am I doing 3? All right, it's supposed to be 7. 7 goes into 34 4 times. I forgot to write my 4 here. 7 times 4 is 28 with a remainder of 6. And then 7 will go into 63 9 times. My apologies there. And then 49 is 7 times 7. And lo and behold, look what happened. We have 3 2's. And we have 3 7's. So that really means if we have a cube root, that means 3 times 3 times, why am I doing 3? Cube root of the 2's repeated times 7 times 7 times 7 is equal to, and these 3 2's come out and become 2 because the cube root of 8 is 2. And 7 times 7 is 49 times 7 is 343. And I'm dyslexic because this is not 334, it's 343. And so these 3 7's become 7, so that equals 14. So the cube root of 2,744 is 14. Factor tree and look for 3 of a kind. They come outside, multiply them together. If there's any leftovers, they have to stay in the radical, and that means they're not perfect cubes, but that did not happen here. Okay, now we have exercises here, so try these, pause the video, see if you can do them, and when you come back, I will explain. All right, so here we go. Find the positive value of x that makes each equation true. Again, positive also means principal root, and check your solutions. So now we have an equation. So remember, we have PEMDAS to simplify expressions. And then if we take the inverse of that and we take PEMDAS and spell it backwards, then that is the inverse operations to move across an equal sign, and we use inverses. Okay, so if I have x squared equals 169, and it says explain the first step in solving this equation, I would say, okay, well, I need to get rid of this square. That's an exponent, so I need to do the inverse of the exponent. So I need to take the square root of both sides. Okay, so now it says to solve that equation and check your answer. So now I will do that. So we have x squared equals 169. I'm going to take the square root of both sides. And the square root of a square cancels, and I get x. And the square root of 169 is 13. And it says to check. So then I'm going to take 13 squared equals 169. And 169 equals 169, and it checks. Number 2. Now it's saying a square is in the shape. A square-shaped park has an area of 324 square yards. Okay, remember what I said. When they say they're given an area, that is what's under the radical. So they're saying area of a square is side squared. So I write a formula, step 1. Step 2, substitute in the givens. 324 yards squared equals s squared. So I'm going to take the square root of both sides. And when I do that, the squared and the square root cancel, and I'm left with s. The square root of 324, if I come over here and do my factor tree, 2, 1, 62, 2, 81. Now I see a perfect square. That's 9 times 9. So I have a pair of 2's and I have a pair of 9's. So that gives me 1 outside. 2 times 9 is 18. So it's going to be 18, and the square root of yards squared is yards. So the dimensions of the park are 18 yards by 18 yards. Okay, squared. Number 3, 625 equals x squared. So I rewrite the problem first. I want to get rid of that x squared, and the inverse of squaring is taking the square root. I get x equals, and the square root of 625, if you don't know that, always do a factor tree, factor out of 5. 5 goes into 6 once, the remainder of 1. 5 times 2 is 10, remainder 2. 5 will go into 25 5 times. 5 will go into 125. 5 goes into 12 twice. 5 goes into 25 5 times. And then 5 is 5 times. 25 is 5 times 5. So I have a pair of 5's, and I have a pair of 5's. So that's going to equal 5 times 5. So 25 equals x. Number 4, a cube. So now we're talking about a cube again. So if I draw a cube, there's my cube. It says the volume equals s cubed in this case. That's my formula for a cube. Sides times side times side. So the volume is my given. It says it's 27 cubic inches. So it says a cube has a volume of 27 cubic inches. What is the measures of one side? And write it and solve an equation. So I'd write 27 inches cubed equals s cubed. And again, to get rid of a root, we have to take get rid of a exponent, we have to take a root of the same index, and that's a cube root. So if I'm cubing, I'm taking cube roots. So the 3 and the cube root and the cube cancel, and I'm left with s. And the cube root of 27 is 3. 3 times 3 is 9 times 3 is 27. So this has a length of 3 by 3 by 3. And inches cubed, cube root is just simply inches. So what is the measure of one side? So the measure of one side is 3 inches. Number 5, what's the positive value of x that makes the following true? So again, we're just going to keep going here. X squared equals 64. I will speed it up now, so try these, pause, and come back, but I'm going to go through these fairly quickly. So it's a square root. I want to do the inverse, which is, or it's a square. I want to do the inverse, which is square root, and the square root of x squared is x, and the square root of 64 is 8. Okay, it says to explain, but if I do this, then I can say that the square root of 64 equals the square root of 8 times 8. So therefore, that equals 8. Because 2 underneath a radical, the number out here tells us how many we need underneath to make 1 outside. All right, number 6. What is the positive value of x that makes this true? It's a cube. So to solve cubes, we do the inverse of cubing, which is cube rooting. So I take the cube root. Do not forget these 3's, because the square root will not give you the same answer. And I take the cube root of x cubed, I get x. And 64 is 2 times 32, which is 2 times 16. And there's 2 times 8, and 2 times 4, and 2 times 2. And I'm circling 3 at a time to see how many I have. So that equals 2 times 2, because I get 1, 2 from each group of 3. So therefore, x equals 4. All right. Find the positive value of x that makes this equation true. X squared equals 256 to the negative 1. Now we're going way back to Module 1, back in September or even August, and we cannot have negative exponents. So the rule says to take the inverse, so think of this as over 1. So x, this is going to equal 1 over 256 to the positive 1, or just 256. So I have x squared equals the square root of 1 over 256, and to solve for square roots, I take the square root of both sides, and I get x equals. Now, if I have a fraction under a square root symbol, then I can distribute that square root to the numerator, and I can distribute that square root to the denominator, and I can split it up like this. And the square root of 1 is 1. And the square root of 256 requires a factor tree unless you know your values. 2 goes into 2 once, 2 goes into 5 twice, remainder of 1, 2 goes into 16 8 times, and that breaks down to 64, and now I have 8 times 8. So I have a pair of 2's, I have a pair of 8's, so that leaves me with 1 8 and 1 2, which equals 16. So my answer is x equals 1/16. Number 8, x equals, or x cubed equals 343 to the negative 1. So it's going to be x cubed equals 1 over 343 to the positive 1. And I'm going to take the cube root of both sides. Do not forget your index. We're doing cube root this time. And that's going to leave me with x equals the cube root of 1 over the cube root of 343. Well, the cube root of 1 is 1, and 343 is 7 and 49 and 7 and 7 from earlier. I have 3 7's, so my answer is 1 over 7. Number 9, is 6 a solution to this equation? Explain why or why not. So when we're given an equation and they're asking if a number is a solution, then we substitute that value in for every x we see. So I'm going to substitute in 6 squared minus 4 equals 5 times 6. 6 squared is 36, minus 4 equals 30. 36 minus 4 is 32. 32 does not equal 30, so no, it is not a solution. Okay? And since 32 doesn't equal 30, then that is not the answer. Okay, that is the end of Lesson 3. Review the lesson summary and go to your problem set.